Okay, so let's see. So a thing that is a little non-intuitive is that less massive stars last much longer than really massive stars. Some stars that are maybe 10 to 15 times the mass of the sun have much shorter lifetimes. So the sun is expected to, live for about 10 billion years. Some really massive stars are maybe going to last a billion years or even less, hundreds of millions of years. Whereas stars that are less massive than the sun, much less massive, basically there are some of them that are, like they're called M-class stars, are so have so little mass that there hasn't even been enough time in the age of the universe for them to go through their life cycle. And so the universe is 13. Stars started forming about 13 billion years ago, and there hasn't been enough time for them to completely go through, some of them to go through their life cycle. All right. There's this magnitude scale that was invented a long time ago, and this is well before telescopes came along, and there's this apparent magnitude scale goes from positive numbers all the way into the negative region. But here's the way it works. The more negative something is, the brighter it is, and in fact, when you're in the positive side, the smaller the number. So, for example, a first magnitude star is brighter than a second magnitude star, and a second magnitude star is brighter than a fifth magnitude star. All right, so the difference in how a star looks is, of course, related to the amount of light that it produces, the size of the star, and of course the distance to the star. All these things affect, how bright what's called the apparent magnitude. So a star might be really bright, but it just is much closer than another star that is, for example, much larger and producing a whole lot more energy. Okay, so what astronomers did is we invented this thing called the absolute magnitude scale, and this is defining the brightness of a star at a standard distance, and the standard distance is, this is where parsecs come into play, is 10 parsecs away. So if you imagine, a star, and you measure how bright it is, its apparent magnitude, and then how bright would it appear if it was 10 parsecs away, and that's about 32.6 light years away. All right. The luminosity of a star is the total energy, as it says here, radiated into space per second, and it's directly related to the absolute magnitude. What we generally do is we use the sun. All stars are compared to the sun, because we know the sun is, of course, the closest star to us. We know the most about it, and so a star whose luminosity is exactly equal to the sun is said to have one solar luminosity. And ones that are much brighter than it, you can have stars that are 100 times brighter than the sun, 1,000 times, 10,000 times, even higher, and then stars that are like a tenth as bright as the sun, or even 100th. All right, the temperatures of stars. So there's this thing called the peak wavelength, and that would be this area here on for this particular star. So all stars are what we would call perfect black bodies, and so a black body is a perfect emitter or absorber of energy. And so when an object is hot enough to glow, it gives off this characteristic black body curve, and this is that curve where there's one peak wavelength. For example, this one peaks somewhere in the in the violet, or even in the, maybe a little bit in the ultraviolet. Whereas like this star right here, which is more closer to what our sun is a yellow star. It peaks right around the yellow, and then another star, would peak. This one down here would peak in somewhere in the red region. It turns out that stars that peak in bluer colors are hotter than a star that would peak somewhere in the middle of the rainbow, and then a star that would be peaking in the red, a reddish star or an orange star, would be even cooler than that. So a red star would be cooler than an orange star, but an orange star would be cooler than a yellow star. Of course, our sun is a yellow star, and the classification of the stars goes like this. O stars are the hottest of them all, and then comes B stars, A stars, F stars, and then our sun is a G-type star, so that that's where we are, and then K stars, and then M stars, and there's actually two more, L and T, but for the purposes of this, we'll just leave it at that. All right. And there they are. They're showing the temperature range of the O stars, the B stars, the A stars, and so forth. Notice our sun is about 6,000 Kelvin, or a little less than that actually. The surface temperature is. Okay. So now here is an extremely useful tool that astronomers discovered, and this is called the HR diagram, or the Hertzsprung-Russell diagram. And what it is plotting the luminosity or the absolute magnitude. Remember, they're directly related to each other. So the luminosity on the vertical axis and the temperature on the horizontal axis, but it's backwards. The temperature is backwards than what you would think. Normally we start at the origin and then we get larger and larger numbers along what's traditionally called the x-axis. But this is the reverse of that. The temperatures are much higher here. For example, this is around 10,000. I'm sorry, it's even higher than that. For O stars, and then down here, for example, for a G-type star, like where the sun is, the temperature is about 5,000 Kelvin. Okay, so it goes down as we get further and further from the origin, and the brightness goes up as we go higher and higher. And there's a couple of things that astronomers noticed about this right away. The vast majority of stars fall along this curving line, which is called the main sequence. And most of the stars in the galaxy, most of the stars in other galaxies fall along this line. And it turns out that this picture, this is basically a snapshot of stars at different points in their evolution. So stars that are converting hydrogen into helium, you find along the main sequence. Like we already know that the sun's going to be there for a good 10 billion years. The stars way up here, because they're hotter, they're the higher temperature, they're not going to last. They're not going to stay on the main sequence for as long. But when a star leaves the main sequence, it becomes one of these giant stars, red giant stars. There are also kind of orange color giant stars as well. And so when a star leaves the main sequence, it's actually heading towards the end of its life, and what's happened there is it's run out of hydrogen fuel at its core. And so you might think that that's the end, but it's not, because when the star begins to collapse, there's this fight between gravity, the inward force of gravity, and the outward pressure due to fusion, right? Normally hydrogen into helium, but that stops when a star leaves the main sequence. But see, what happens is, and this is the region, the area we call the variable stars. Cepheid variables are one type of these. And so what happens is the star will actually be able to convert to fuse heavier elements. So it'll go to helium and beyond. And when it does that, they can vary in brightness The variation is really the atmosphere of the star expanding and contracting. So anyhow, these are the giant stars up here, and eventually these giant stars will end up, most of them, the vast majority of them, will end up down here in this region, where you have extremely hot stars, high temperature stars, but they are extremely dim. They're much, much dimmer, maybe at 1/100th the brightness of the sun. And this region down here are called the white dwarfs. So three important regions for us: the main sequence, the giant stars. There's a space between the giant stars and the main sequence called the variable stars, but that doesn't last too long. Anyhow, after that, there is this region called the white dwarfs. So this is a snapshot of stars at different points in their evolution. And these are dead stars. The white dwarfs are actually dead stars. Even though they're still glowing, it's like a burning ember. No hydrogen or anything else is being converted into helium, or hydrogen converted to helium, of course, that's something in the main sequence. But then the heavier elements, that's what's being converted, turned from in the cores of the stars, heavier and heavier elements are being created. And then for most of the stars that are around the mass of the sun or less, or even up to about 10 times the mass of the sun or less, they'll end up down here as white dwarfs. And so no hydrogen or any other element is being converted. In fact, these things, the ones that are that become white dwarf stars, they can only fuse up to iron, element 26, and that's it. Okay, so this is just a little. I guess I kind of already did all this. The protostar, it's not technically a star yet. It's still undergoing gravitational collapse, and then when fusion takes place at the core, then it becomes a star. And you have this equilibrium between the inward force of gravity and the outward push due to fusion. And that's until the end of the star. And keep in mind, fusion is only taking place in the core. All right, so this is what I was just talking about, how stars most of them end up as white dwarfs. All right, so for less massive stars, that's what happens. This is what's called a planetary nebula phenomena. So basically, as these stars head towards the white dwarf stage, they lose their outer shells. Some of them will lose their outer shells, and you can actually see that. It's a ring of glowing hot gas that goes out and actually repopulates the gas in the galaxy, so that it basically enriches the gas, because this is full of all sorts of metals. Okay, that what was not in the original gas and dust that made up the galaxy, because that was only hydrogen and helium. All right, let's see. Now, stars much more massive than the sun have a spectacular ending called a supernova, where there's an actual explosion. The core of the star collapses, and then all that material hits itself at the center, and then basically bounces back outward in a spectacular explosion, which you can see. You can actually see supernova in other galaxies. They're that bright. A single supernova can outshine, just for a matter of maybe weeks to months, outshine the rest of the entire galaxy that it's in. And this is the point where elements beyond iron are created. And in fact, that's why that stuff, things heavier, much heavier than iron are relatively rare, because it takes a supernova explosion to create them.